let's take a look at number 3. Sketch and interpret the gradient field for the velocity potential theta equals arctan y over x. So again, we've got theta here, but we could also think of this as z equals arctan y equals x. Theta is kind of nice here for your output because it will represent an angle because we have arctangent. So let's start off thinking about the level curves. What are the level curves of this going to look like? So we need to put a c value in for our output. Now that's a constant, right? That's some constant value. Can you solve that for y? All right, I want you to solve this for y and then graph out some level curves. Pause the video and restart it when you've got that done. All right, did you get something like this? Let's see, when we solve this for y, we get tangent of c equals y over x. So y equals x times the tangent of c. And since c is a constant, this is just a line. And the tangent of c is the slope of that line. And the y-intercept is 0. So if we pick, say, pi over 6 for c, then my level curve at that point, at that level, is root 3 over 3x or 0.6x. So that would be right here. Okay, this is at the level, let me write c. c equals pi over 6. All right, now what about c equal pi over 4? Well, the tangent of pi over 4 is 1. So at the level pi over 4, now we usually don't choose levels to be pi over 4, right? We usually choose our elevations to be stuff like 1, 2, 3, 4, 5. But hopefully you see why it's advantageous to pick angles, because we're plugging them in into the tangent function. It just makes it a little bit easier to evaluate. All right, so there's c equals pi over 4, gives me that line. And this gives me c equals pi over 3. And then I did one more. You know, you could do as many of these as you want, but just kind of getting the idea. C equals 3 pi over 4. And we could just continue. So what we get is a whole bunch of lines going through the origin for our level curves. Now, before we go look at the gradient field, so we're going to do the partial derivatives of this. Before we go do that, let's take a look at this graph. It's a little bit interesting. All right, so in this graph we have z equals arctan y over x. So it kind of looks like this, and you could go mess around with it. Now, I'm pretty sure that's going to be an asymptote right there, but it's just connecting them. There is some place where that's going to be undefined when x equals 0. Right, so okay, so let's look at a level curve. So what I've done here is I've created a c value that can go between 2 and -2, and then I'm going to plot the plane z equals c. So right now we're at z equals 0.3. Now this isn't, you know, we did pi over 4 and pi over whatever, and we could figure out the decimal approximations for those, but this just gives us a picture of what's happening. Okay, so there's my graph. So let's take a look at this level curve. Now, if I look at it this way, see where this level curve is intersecting this graph is at this line right here. Okay, now let's change the level. Oh, interesting. If I go up to a level of 0.6, it's intersecting there. Let's look at it this way. Let's watch it. Let's just let her go here. Oh, that's kind of cool. Okay, so the level curves are intersecting the graph. These negative values down here. It's kind of fun to watch it from up top, and you can see the lines. All right, those are our level curves where those are intersecting just these lines. That's neat. Now if we look at it from the bottom when it's down here, we get the same kind of deal. Okay, so that's what's happening. That's why those level curves are doing that. Let's go back and figure out our gradient field. Pause this thing here. Okay, so we need to do our partial derivatives now. So you need to remember what the derivative of arctan is. So the derivative of arctan x is 1 over 1 plus x squared. All right, so we're going to do our potential function over here as a function of x and y, not our potential function, our vector field, our gradient field. So we're going to have to do the derivative of theta with respect to x and the derivative of theta with respect to y. So we're going to do the derivative of this arctan with respect to x and the derivative of the arctan with respect to y. So we really need to think about the chain rule here. Let's go ahead and do x together. Let's do it over here. Okay, so let's say theta equals arctan y over x. This is a good review. The partial with respect to x then is going to be 1 over 1 plus whatever's in this parentheses here squared times the derivative with respect to x of what's inside the squared. The derivative with respect to x of that. So maybe it's easy to think of that as y equals x to the negative 1. Okay, so what would be the partial with respect to x of this business here? All right, so it's just a power rule, negative 1 y x to the negative 2. So maybe I write that up here. So that's this business, right? And we're doing with respect to x. So let's write negative y over x squared. All right, you do the partial of theta with respect to y. Alright, so you should get 1 over 1 plus the quantity y over x squared times, and then the derivative of the inside part with respect to y is just going to be 1 over x. Right? The partial with respect to y of y times x to the negative 1 is just x to the negative 1. Alright, so now what I want you to do is simplify this business here. This can be simplified. So pause the video, simplify this, and unpause the video when you have it done. Alright, you should get the opposite of y over x squared plus y squared, and then x times x squared plus y squared after you square this out and cancel stuff and simplify. Alright, so we see that we have a common denominator here. We could actually factor that out in front of our vector and rewrite our vector like that. Now, why would I want to do that? Well, this kind of helps me visualize what's happening. We've done this vector field before, right? That is our rotational vector field that we did previously, and it's just being multiplied by some value out here, which is going to change the lengths of those. Now, before we go take a look at this, I want you to think about these level curves right here. Where's the steepest ascent? Okay, like if I was, say, sitting at this point right here on my graph, my 3D graph above this point, which would be the direction of steepest ascent? Right, the next highest level is this curve here. So I'd need to head directly towards that. Okay, now I don't know the magnitude here. I'm just trying to give some direction. All right, what if I was here? I'd want to head directly towards that one. So we can see this rotational field, how it makes sense here. Right, the level curve's going this way. Now, what about the lengths of these vectors? Let's put 2 vectors in here, and you tell me which one would be longer. So let's say I'm sitting here versus here. All right, so the direction of steepest descent is going to be towards the next level curve there, but which one of these vectors would be longer? In other words, steeper. which one would be longer, right? It's where the level curves are closer together because I have, less distance to get to the next height. So this would be longer as I'm closer to the center. It's getting steeper as I'm closer to the center. So if I'm here, this is going to be not quite as steep. This is going to be not quite as steep, right? And as I go out here, it's not steep at all. So we get, sorry, those should be more, in a line. But that's the idea, all right? That makes sense. We should see something like that. We should see the vectors closer to the origin longer because it's steeper there, and the vectors further from the origin shorter. So let's go take a look at that. Alrighty, so here's the vector field. I'm going to scale this. I'm going to zoom in on this a little bit. There we go. So we get this, we see these vectors close to the origin are very long. They're still rotating. It looks like they're sort of rogue, but these four vectors are still rotating. And if we increase the density, we can see these a little bit better in here. These are the ones that looked like they were rogue a second ago when we had less density. These ones. Now I'm going to do more density. Okay, watch these ones. So we get a whole bunch of them in here, and then we get new ones that look like they're rogue. But if we graphed a bunch of those, they would show rotation as well. Alrighty. So that's a pretty cool example of a vector field as a gradient field for a particular surface in space.